Today, we're going to have a look at open domain question answering and how we can fine tune our own retriever model to use for open domain question answering. We're going to start with a few examples. Over here, we have Google, and we can ask Google questions like we would a normal person. So we can say, how do I tie my shoelaces? So what we have right here is three sort of components to the question and answer. And I want you to remember these because these are relevant for what we are going to be building. We have a query at the top. We have what we can refer to as the context, which is the video, which is where we're getting this small, more specific answer from. And we can ask another question. Is Google Skynet? So we have a question at the top, we have this paragraph, which is our context, and then we have the answer, which is yes, which is highlighted here. So it's slightly different to the previous one where we had the video. This time we have actual text, which is our context. And this is more aligned with what we will see throughout this video as well. Now, what we really want to be asking here is, one, how does Google do that? And more importantly, is why should we care? Now, we can imagine this problem as us being in a really big warehouse. Now, we don't know anything about this warehouse. We just know that we want a certain object. Now, we don't know the specific name for that object. We just kind of know what it looks like. Now, in this warehouse, everything we assume is probably going to be organized in some way. So the first thing we're going to do is have a look at the products around us and try and figure out if there's some sort of order. And once we have figured out how this warehouse is structured and how we can search through the warehouse, we need to figure out, okay, everything is maybe organized based on the name of the product. We don't know the name of the product. We're kind of going to struggle a lot, and we're going to spend a lot of time searching through a lot of items in order to find what we actually want to find. That is like a normal traditional search experience where you have to know the exact keywords that you will find with whatever it is you're looking for. You have to know the product name. Now, this sort of natural language search that we just saw with Google is not like that warehouse where you're just alone trying to figure out how it's structured and how to search through it. Instead, it's almost like you have a guide with you, someone who knows this warehouse. They basically live in this warehouse. They know where everything is. And if they don't know where a specific object is, they can point you in a pretty good direction and really help you find everything probably a lot faster. Because as well as knowing where everything is, this person also speaks the same way that we do. We can ask them a question like, okay, guide, where are those marble-like things? And with that, they will hopefully be able to guide you in the right direction. And maybe they'll be able to guide you right to that product, or at least in this area that they are found in. So that's the difference between traditional search and a question and answering search. Now, don't get me wrong, there is places where you do want to keep a traditional search, but particularly for unstructured like text data, or as we saw earlier, video and audio data, this sort of Q&A approach can be really powerful. So that leads us on to the second question, or first question I asked, which is, how does Google do that? Now, Google is pretty complex, but at the core of what we saw there was something called Open Domain Question and Answering, or ODQA. Now, ODQA is a set of language models and technologies all piled together into a open domain question answering pipeline. Now, that pipeline, at its simplest, will look something like this. So we have our, let's say at the top, we have our question. That question is going to come down here and it's going to hit what is a retriever model, which is what we will train or fine tune in this video. Now, this retrieval model, that will handle taking our query and converting it into a vector. Now, we convert it into a vector because then we compare it to other chunks of text, and we can encode the semantics and meaning behind that text rather than just the keywords. So that's why we can search for concepts and meaning rather than just keywords, as I mentioned earlier. So we have this retrieval model. Now, the retrieval model creates a vector, but then we need something that allows us to search. So we need other vectors to compare to. Now, where do we store those vectors? Well, we have a vector database. Now, a vector database, let's bring that over here. This is going to contain context vectors. So you remember earlier on with those Google searches, we had the question, we had the context and the answer. This is where that is relevant. So in here, we have loads of context. So I'll just put C, but they've all been converted into vectors using the same model we have up here, the retrieval model. We just did it before we started searching. So we indexed those contexts into our vector database. Now, at search time, we convert our question into a vector, and that comes down into the vector database, and the vector database will compare that question vector to all of these context vectors, and it will return the ones that are most similar. So maybe we want to return the top 5 most similar contexts. At this point, if we are just using a retrieval model and a vector database, we can return those. We had our question and we can return these contexts to the user. So that would be like in our earlier examples, we ask a question and Google returns like a page, or it just returns a paragraph to you rather than the highlighting the specific answer. And these are the components that we're going to cover today. And in a future video and article, what we are also going to include is a reader model. So a reader model is added onto this open domain Q&A stack, or it's the last component of the stack. And what this does is it takes each of your context vectors and it reads them. So it has a look at the context vectors, and we have this long text here, and it says, okay, given the question, which we also feed into our reader model, I think the answer to that question is right here. Okay, so it allows us to extract a very specific answer from a longer chunk of text, the context. So that's the open domain Q&A structure or pipeline. And now I think we should move on to actually fine-tuning the retriever component of that pipeline. The first thing we need to think about when fine-tuning our retriever model is whether or not it actually needs to be fine-tuned, because there are retriever models out there already that we can just download and use. And there's this really good concept that I saw in one of Nils Reimer's YouTube videos where he's giving a talk, and he talks about the long tail of semantic relatedness. And the basic gist of it is that you have common knowledge that pretty much everyone knows about, and you have a lot of data and benchmarks in that area. So that would be our cat versus dog example up here. So imagine you're on the street, you walk up to a stranger, you ask them a question, what's the difference between cat and dog? They're probably going to know the answer. Everyone knows that. Then you get more specific. So you ask them, okay, what's the difference between C and Java? Some people will know, some people will not. And then we get even more specific, PyTorch versus TensorFlow, and then we get even more specific, Roberta versus dBERT, and then TSAE versus MirrorBERT. As we get more specific, less and less people know what you're talking about. And with that, there are less data sets and there are less benchmarks. But at the same time, that's where most of the interesting use cases exist. Now, whether your use case exists within the common knowledge area or within the sort of the long tail is really how you can hazard a guess at whether you need to fine tune a retriever model or not. So if we just modify that chart a little bit, we get this. So we have same thing, common knowledge on the y-axis. And what we have on the right, I've just renamed it. So the ease of finding a model and or data. Okay, so based on how niche your use case is, the harder it is going to be to find data for that niche. And the less data there is out there, the less likely someone else has already trained or pre-trained a model. So most of the pre-trained models out there are trained on a very generic, broad range of concepts. Like they're trained on Wikipedia pages or something like that. So that's fine. You know, if you're comparing cats versus dogs or even C versus Java, the model is probably being pre-trained on something similar to that, and it might be able to figure it out. But if your use case is more specific, like you have, I don't know, like some very specific financial documents or technical documentation, something along those lines where not many people understand the content of that documentation, and there's not, you know, it's not general knowledge or it's not easily accessible on the internet. In that case, you will probably need to train or fine-tune your own model. So if that is the case, how do we do that? Well, to train a retrieval model, we need pairs of text. So we need questions and relevant context. So that's what you can see here. We have question A, context A. They're both related and they both end up in the same sort of area. That's what we need to teach our retrieval model to do. We tell our retrieval model, okay, question A and context A. Process them and output a vector for each one of those. And then we want to look at those two vectors and say, okay, are they similar or not? If they're not similar, we tell the model, look, you need to figure this out and make them more similar. If they are similar, then great, good job. That's what we're optimizing on. We're optimizing on minimizing that difference between similar pairs and maximizing the difference between dissimilar pairs. Now, our data is going to just contain all of these rows where we have the question and context pairs. We don't need labels because we are going to be using multiple negatives of ranking loss, which we'll discuss in a minute, but there's also a video on that if you do want to go into a little more depth. So to train our model, we're going to be using the Squad 2 dataset from over here. And in there we have our questions and we have context. Okay, that's what we're going to be training on, those two pairs. So let's take a look at what that process looks like. So as I said, we're going to be using the Squad V2 dataset. We're going to be pulling that from Hugging Face datasets, so you may need to pip install datasets if you do not have that already. And this is how we load the dataset. So we've got Squad V2, and we're getting the training split of that because there's also a validation split that we will use later. And from there, what we will see is we'll get an ID, title, context, the question. So only the question and context is really that important for us. So we can go down and just a few examples here of different samples or rows from the dataset. And like I said before, we need to take the question and context pairs from the dataset. So to do that, we're taking them here. We're also creating this input example or list of input example objects. Now, input example is just the data format that we use when we are training with the sentence transformers library, which you can see here. Now, again, if you do need to install that, it's just pip install sentence transformers. And TQDM is just the progress bar that you see down here. That's all. So what we're doing is just appending a load of input examples where we have the question and context. We don't have any label here because we are going to be training with multiple negative ranking loss where we don't need labels. Now, Also, because we're using that type of loss, MNR loss, we need to make sure that each batch does not include duplicates. Now, the reason for this is when we train with MNR loss, we're going to be putting everything or training in batches. And the model is going to be looking at two pairs like this, and it's going to take the question and it's going to say, okay, for that question, this context here needs to be the most similar, and all of these contexts need to be as dissimilar as possible. Now, the problem with if you have duplicates in your batches is that you have, let's say, this exact same, maybe not the exact same question, but you have the exact same context down here. Now, your model is going to be optimizing to make all of these as dissimilar as possible, but also this one here, even though it's exactly the same as the one that's optimizing to be more similar. So you really need to try and avoid this. It's okay if it happens occasionally in the odd batch, but you need to avoid it as much as possible. So that's why we use this no duplicates data loader. This will make sure we don't have any duplicates within each batch. So we'll go down. We need to initialize a sentence transformer. Again, this is the same as what we usually do. I've written BERT here, but we're actually using the Microsoft MPNet model. Now, MPNet is really good for sentence transformers in general. If I did this with a BERT model, I think the performance is 2 percentage points less than if I use a MPNet model. It's not huge, but it does make a difference. So it's good to try both if you want, but this one is the one I'd go with. So here we've initialized the model. We also have this pooling layer. Now, the pooling layer is important. That is what makes it a sentence transformer rather than just a normal transformer. And it works like this. So we have our sentence. It will get tokenized and split into many tokens all down here and put into BERT, MPNet, or some other transformer. And on the output of that, we get all these token vectors. Now, all these token vectors represent our sentence, but there are loads of them. We want a single vector to represent a single sentence. So we use this pooling layer. And this pooling layer takes all of those vectors and takes the average in every single dimension. So we take the average and we get our sentence vector. That's both how and why we use the pooling layer. So we have that, and we can come down and we see we have our transform model, we have the pooling layer. It's good. Like I said earlier, we are going to be using MNR loss for training, and that does the batching thing where we want to get the pairs together and then we rank all the other contexts as dissimilar. So we initialize it like this using the sentence transformers library, and then we're ready to train our model. So it's really not that complicated, particularly if you're using sentence transformers library, it's very easy. So we warm up for 10% of the training steps. That's a pretty standard number for sentence transformers. You can modify it a little bit, but 10% is usually pretty good. It just helps make sure we don't overfit. And the same for epochs. Almost always set that to 1 when you're fine-tuning sentence transformers. Otherwise, it really does tend to overfit. So it's usually a good idea. It shouldn't take too long to train. It was 30 minutes for me here. It might take a bit longer, but really it's not training on too much here. I think we have like 100,000. No, I think we have 130,000 training samples in the squad data. Now, another really important thing is evaluation. So once we've trained our model, how do we know that it actually works? Like, is it performing well? We don't know. So we need to measure how accurately our model is retrieving the correct context for a particular question, which is slightly different to other operations or evaluation metrics that we use with other language models. And to evaluate the retrieval performance, we use this information retrieval evaluator. Now, from this, we're going to be using the map at K metric, which is, in short, an average precision value or fraction of returned context that are relevant to the question we asked. And the at K component of that is just saying we are going to consider the top K return results. So if it's at 10, as in K is equal to 10, we're going to return 10 contexts, and then we're going to calculate that metric from those 10 return contexts. Now, by default, this evaluator is going to be using that map K metric. So we initialize it like this, so information retrieval evaluator, and it needs data. We're going to be using a validation set of the same data we used before, so the squad v2 data set. And it looks the same. Okay, we have ID, title, context, question, answers. At the moment, we're going to need ID, context, and question. Now, this evaluator needs us to map relevant questions and contexts using those IDs. So what we're first going to do is we're going to convert this into a pandas data frame. So I find it a little easier to work with for what we're going to be doing here. So converting it to a data frame here, we can see we have context, ID, question, which is all we need. Now, we need to assign a specific or a new ID to the context. Because at the moment, if you look here, we have an ID and it's shared by the context and also the question. And another thing is the ID for the context, like here, even though the context is the same, the ID is different. So what we're going to do is use these IDs for the questions, because all the IDs need to be unique. And we're going to create a new ID for each context. So we're going to deduplicate that data frame. So we have question and ID, nothing else. And then we're just going to append this con onto the end of our ID. So now we have unique IDs for all of our contexts as well as our questions. And what we can now do is merge or form an inner join with our no dupes data frame and the original data frame. So we do that. And now we have a unique ID. So this ID Y for each of our contexts. So you can see ID Y is not changing where we have these duplicate contexts. And then we have IDX for the questions. So this is what we need for our evaluator. So we need to reformat this into 3 different dictionaries. So we have IR queries, which is a mapping of question ID to question, like the text. We have IR corpus, which is a mapping of the context ID to the actual context. And we also have IR relevant docs, which is a mapping of the question ID to relevant context ID. So you can have multiple context IDs for a particular question, but in this case, it is actually just a one-to-one mapping. So we first create the IR queries dictionary. So it's literally just the ID as a key and the question as a value. So we create all of those key value pairs. Same again for IR corpus, exactly the same, but this time for the context. And then if we come down here, so this one's slightly different. So this is mapping the question ID to a set of relevant context IDs. Now, we could map these directly, but what I've done here is if you use this same script and you have an example where maybe you have multiple contexts for each question, this will handle those. And so you'll get a list or a set of multiple context IDs in here rather than just one, if that is relevant. And we see that we have multiple, in our case, we have multiple questions that map to a single context ID. So it's actually many to one rather than one to one, like I said before. Now, with each of those 3 dictionaries, we can initialize our evaluator, which is we just pass them like this, and we evaluate. That's Really simple. There's nothing else to it. And the map at K performance for that is 0.74, which is good. If we compare it to like some of the state-of-the-art retrieval models, so this is also using MPNet, and it's been trained on a lot more data, by the way, as well. So it's more general. This is getting 76%, so a little bit better than ours, like 2 percentage points better. But this is the squad dataset. This other model here I'm pretty confident, has been trained also on the squad dataset. So it has already seen that data. If you do the same thing, but for your own more niche dataset, I think most likely you will get a model that outperforms any other pre-trained models. But of course, definitely just test it, evaluate, see what you get. Okay, so we have fine-tuned our retrieval model now, but we can't really use it unless we store the vectors that we create with our retrieval model somewhere. So we need a vector database. Now, to do that, we need to take a few steps. So we have already done a few. Okay, so we have trained our retrieval model, so we can maybe cross that off. We've also downloaded a load of context, so the squad context. We'll use a validation set for that. Okay. Now, the next step on this side is to encode those contexts, which we will do in a moment. And then over here, we also need to initialize our index for our vector database. So we're going to do that. And then we're going to take those encoded contexts and our initialize index, and we're going to populate that index with our encoded context vectors. So let's get started with that. Okay, so I'm in a new notebook now. So if you're following along and maybe your model is still training or fine-tuning, that's fine. You can actually just download the model that we trained here. So it's just Pinecone, MPNet Retriever, Squad 2. That's the model that you saw a moment ago. If you want to try the BERT one as well, you can replace this with BERT, and that's also there. So we have that model. We can see it looks the same as what we had before. And I'm also just going to reload the validation data set. Now, I'm going to extract all of the unique context, because we have, like we saw before, the squad data has many copies of the same context, and we don't want to have duplicates in our index of the same vectors, because if we're searching and we compare the distance between our query vector and all these contexts, and we have like 5 that are in the exact same position, we're going to return all of those. So we don't want to do that. So we need to remove duplicates. Okay, so we're looping through the whole data set. We're checking if context is already within this unique context list that I've initialized. If it isn't, we add it to that list. And we also add the ID. Remember the question ID, context ID was shared. All right, we're just using that ID this time. We're not using the unique context IDs that we created before. So we loop through, and then obviously when it sees that context again, it's not going to add that different ID to the unique IDs list. And then we can filter using the Hugging Face datasets library here to only keep the IDs or the rows which have an ID from the unique ID list. So with that, we end up with just one of each context. And you can see here we only get 1,200 rows out of that, which is much less than the full squad validation set. Now, what we want to do is encode those contexts into context vectors. So we use our model that we've initialized, and we use the encode method. Now, we also convert that vector. So this, I think, outputs a PyTorch tensor. We convert it into a list, because we are going to be sending all of this to our Pinecone vector database index through an API, and for that, we want to have them in a list format. So we encode the context, and now we can see, okay, we have all the other features that we had before, but now we also have the encoding feature. So we move on to the vector database. Now, how do we use this vector database? We first need to install the Pinecone client here, because we're going to be using the Pinecone vector database. So we come down and we can import Pinecone. So this will just import the way that we interact with our Pinecone vector database. And we then initialize a connection. So for this, you do need a free API key. So it means free. You don't need to pay anything for that. So you just go to app.pinecone.io and you create an account. And then with the API key that you're given, you enter it in here. So just in there, Pinecone init API key. And you also set your cloud environment, so US West 1, GCP. And then what we can do once we've initialized that connection is we create a new index. So to create that index, we only need this little chunk of code. We need this .create index method. And we specify the name of the index. I'm going to just call it squad index. You call it whatever you want. And the dimensionality of our vectors as well. So you can see here it's 768. And you can also define the metric. Now, you could also use Euclidean distance, but we are going to stick with the default, which is cosine. And yeah, that's all you need to. You only need to run this, but at the same time, because I have multiple indexes and I'm sort of rerunning this code and testing it, I added this in. So I'm just saying if squad index is not already existing. So I'm checking that it is not already running that and then creating it. And then we connect. So specifically to our index or on just our Pinecone database as a whole, we connect. So we use Pinecone index and specify the index that we'd like to connect to. And then from now on, we just use this index object for everything we're doing. So here we are just preparing our data to upsert into Pinecone, which is just upload into our Pinecone index. So when we are uploading data into Pinecone, we have sort of three components. We don't need all of them, but I'll go through them. So we have a list, and within that list, we have these tuples. In there, we have the ID of the vector or the entry record, whatever. And then you have your encoding or the vector itself. And then optionally, you don't need to include this, so you can remove it if you want. You have a dictionary of metadata. So this is just key value pairs that you can use for things like metadata filtering, or if you want to return a particular piece of data with your search, you can include that in there as well, which is what I'm using it for here. Now, you don't need to do this. You could store the text locally, but I'm just doing it like this because it's a little bit easier for this little script. And with that, we just upsert. So we just run this index upsert. I'm doing it in batches. You can probably increase the batch size here, but I'm just sticking with that. And it is reasonable. It's pretty quick anyway. So 13 seconds, it's no problem. So with that, our index, so our vector database and our retriever are ready. So we can actually begin querying and asking a question and returning a relevant context. Okay, so we're on to another notebook for this. So again, I'm going to initialize a retriever model, and I'm going to import Pinecone, initialize the connection to the index, to the squad index again. Now, this is pretty straightforward, fortunately. Now we're at the end. All we do is we take a question. So I'm going to say, when were the Normans in Normandy? And we just write this. So model and code. We include our query within a list here because, for example, if you had multiple queries, you might have that in a list, something else up here. And in that case, you would not have to add these square brackets. But in this case, we just have a single query. And we create a PyTorch tensor. which is our query vector, and we convert it into a list because we're going to be sending it through the Pinecone API again. And what I'm doing here is I'm querying. So this is going to the Pinecone vector database. I'm querying, I'm saying I want to find the most similar vectors or context vectors to this query vector or question vector. I want to return just the top two contexts that you find. And I want to include a metadata in that response, because in the metadata I included the text. So we can come down here and we see, okay, this first example isn't actually what we want. So in here, what we're asking, when were the Normans in Normandy? This doesn't actually answer that question. But then the second one, so if I open this up in the text editor, so if I come down here, we have the second question. So the Normans were the people who in the 10th and 11th centuries gave their name to Normandy. So we can assume that they were probably in Normandy in that time. So that's when they were there. So we get the correct context in second position for this one. We also get the scores, so we can see it's a good score, it's high. And then we have another question here. So we've got three questions. We'll go through each one of those very quickly. How many outputs are expected for each input in a function problem? And we do actually return the correct answer for that one straight away. So a function problem is a computational problem where a single output is expected for every input. So that's our specific answer there. Okay, we get a really high score for that. So it's pretty confident that this is correct. And then the lowest score for the other ones where the actual question is not answered. So one final one here. So I changed the wording a little bit for this one because I don't want to be just doing a keyword search. So I put who used Islamic, Lombard, etc. construction techniques in the Mediterranean. And I modified that a little bit, and we do actually return the correct answer straight away. Confidence 0.6. If you compare it to the other ones, which are much lower, that's pretty good. There's a good separation there, which is what we want to be looking for. So that is I know it's pretty long. There's a lot of components and moving parts there, but that's the open domain question and answering pipeline, or at least the vector database or retriever components of that. And we've also had a look at how we can fine tune our own retriever. So we've covered quite a lot. So, with all of that, you're ready to just go ahead and implement what I think are probably two most crucial components in open domain question answering. If you don't have a good vector database and good retriever model, you are going to be returning not good context to your reader model. And if you don't have good context for your reader model isn't going to give you anything good. So these two are probably the most important parts, right? If your reader model is rubbish, maybe it gives you a kind of weird span or answer, but at least you've got a good context to go off of. So your users are at least getting some relevant information. Now, I think one of the coolest things about open domain question answering is just how widely applicable it is. Basically, any company across so many industries across the world can use this if they have unstructured data that they need to essentially open the doors to for their staff or their users. Right? If you want to get data or information to someone, which is a big part of most jobs, if you want to get data, information to someone more effectively and using a more natural form of search and question answering, this is probably applicable to you and maybe your company. Anyway, that's it for this video. Thank you very much for watching. I hope it's been useful, and I'll see you again in the next one.